The goal of the project was to create a device that holds an anesthetized mouse in place while applying a 3-point cyclic load to the tibia to mimic the force of walking, so live osteocyte reaction can be imaged by a microscope. The best in vivo results for osteocyte calcium responses take place in live bone, which has never been imaged before in a natural environment under a given force. Osteocytes sense the forces exerted on bone and orchestrate bone formation in response. Osteoblasts are responsible for building the bone. It is necessary to use live mouse bones to get true results on the calcium response because the signal of a cultured bone is much lower. There is little known about cellular response in natural bone repair due to this constraint and the response of osteocells ex vivo. Cells have been imaged after being removed from the body but not in their natural environment. This causes changes in cell shape and function, leaving little data on accurate representation of cell function. The study of calcium responses in bone can help improve on many different bone diseases like osteoporosis, which results in bone loss and increased risk of fractures that can lead to death due to the balance shifting from bone formation to bone resorption as one gets older.
This is a side view of an AccuScope EXI 310 inverting confocal microscope, which was used to model our design. Key features to consider are the clearance between the imaging camera and the ability to remove or attach components directly to the microscope stage. A 52mm 4-ohm speaker is used to provide the adequate force. The loading arms are fixed to the speaker cone using a high-strength adhesive and are machined out of high-strength to weight ratio aluminum rod. The standoff post and platform are optically clear polycarbonate. The cage design can be scaled to fit a variety of animal models when importing the STL file to a 3D printer. As the speaker cone moves, it applies a downward force to actuate the loading arm onto the mouse tibia. The cyclic loading will be comparable to the force while walking. The speaker cone is secured to the loading arm, which is precisely calibrated for frequency, displacement, and force, which are measured and tested using an Arduino program, height and dial gauges, and a load cell. The frequency, displacement, and force can be optimized to fit a specific research requirement. For example, a mouse would require a larger force at a faster frequency to simulate running. The cage houses the mouse during testing to ensure there is easy access to the tibia for alignment into the focal window of the microscope. The open design allows for a heating pad to maintain specimen temperature throughout testing. The cage is also meant to reduce the risk of the animal injuring itself or the researcher and reduces the time it takes to secure the specimen and obtain video. This is of particular importance because the small blood volume of the mouse, coupled with a fast metabolism, make it particularly difficult to anesthetize the mouse for long periods.
For the testing portion of this project, a load cell is what will provide the deflection data and force range of the speaker. Calibration of the load cell required multiple tests of the force to voltage relationship. Known masses were hung at the end of the load cell, and the output of the voltage was recorded. A completely linear relationship was established with this load cell. To ensure there is no hysteresis, the load cell was flipped and the same experiment was conducted. To continue testing and to gather information on the deflection, the same testing would be conducted using a height gauge with a dial gauge on the end. With using such a small force on a small object, you would want the smallest unit attainable to gather the deflection measurements for a given force. The dial gauge allows for this type of precise measurement. When calibrated and placed on top of the load cell, the dial gauge would give you the deflection of the load cell, while the load cell is providing you with the given force being applied at the same time. After calibration, the speaker values would be obtained by a set voltage output from the waveform generator to show the force on the cell for actual testing. For our conclusions and future work, our main goal would be to test our design on live animal models at Henry Ford Hospital. Some future work would be to attach a screen to the Arduino for more convenient use and feedback of real-time deflection and force data. Some more future work would be to evaluate other research areas this product could be used in due to the adjustable frequency.